So what's the agenda for today, for this session? First of all, we will talk a little bit about the open loop transfer function and the closed loop transfer function and the loop gain. Then Florian will explain measuring of the loop gain, what is the voltage injection method, how big should be the signal size, the injection signal, then how to choose a correct injection point and some practical examples as well. And then we will explain how we can measure the plant and the compensator. After that, we will do some short hands-on live measurements. There we will measure the loop as well as the plant and the compensator, and in the end we will do a step load response measurement. So now I will hand over to Florian, who will start with the DC-DC converter system.
Thanks, Tobias. So today we are going to talk about the dynamics of DC-DC converters, or actually power systems or power converting systems. And in the reason why we do that, I think it's quite clear. If we have a system like that, so in this example a boost converter, and we want to analyze how will that system react to dynamic changes, that could be a sudden line voltage change or a change in the reference voltage point or in the set point, how will that system react? So if the input voltage changes, how will the output voltage change? Or if the duty cycle changes, how will the output voltage change? So that's the questions that we want to answer by analyzing the dynamics of the system. Then, of course, this is also correlated to how to design the compensator, how to place the poles and the zeros such that you get the desired dynamic behavior. We won't cover the compensator design in detail today. That's too much for this 1 or 1.5 hour webinar. But basically, normally you take the plant transfer function and then you choose a compensator to get a loop design or a loop transfer function that has the crossover frequency and phase margin that you need. So, but we'll come to that later. Normally dynamic modeling is used. That can be quite challenging to create the dynamic models of such systems. I mean, for a buck, for a boost and for a buck boost, you will find the models in literature. But if the system is more complex, if the plant is more complex, or if the control scheme is more complex, then the modeling gets more complex, and it makes sense to verify the design after you build up the first prototypes, of course. You can do that either in the time domain by doing a step response, or in the frequency domain by measuring the frequency response, which makes absolutely sense because the design is normally also done in the frequency domain. So let's jump into the transfer functions. First of all, we're going to look at the open loop plant transfer function. So, and from now on, we will simply assume that the transfer function is equal to the frequency response. But the frequency response, that's what we measure actually. That's just, that has a start frequency and a stop frequency, so it doesn't cover the entire frequency range, whereas a transfer function, of course, covers everything. But in this case, if you assume that S equals j omega, so for periodic systems, we just assume that transfer function and frequency response is the same. So let's see, what do we have? Of course, we have a duty cycle to output transfer function, where the d of S is the change in the duty cycle that enters into the transfer function block. And in this case, we have the GVD, so that means the duty cycle to output transfer function, and the result, of course, is the change in the output voltage. So that describes how changing the duty cycle changes the output voltage. And then, of course, another important one, that's the line to output transfer function, where we say a change in the input voltage, V in, how does that pass through to the output voltage, and that transfer function we call the G in out of S in that case. By the way, no, that's not PSRR, that's a closed loop line to output. Okay, so that's open loop transfer functions. That's a duty cycle to output and line to output with no control system drawn, so the picture is misleading. The control circuit is not yet connected to the plant. We have the duty cycle to output and the line to output transfer function. So let's now close the loop. So here now the closed loop system is correct. So we have a switching converter in the upper diagram, and then we have the input voltage that goes into the switching converter, and then there is the output voltage that is then fed back into the error amplifier. The error amplifier compares the output voltage with the reference voltage, creates the error voltage, feeds the error voltage into the compensator block. There we have the transfer function of the compensator. Then we get the output voltage of the compensator that is fed into the PWM block that creates a new duty cycle value for the next switching cycle. And then, of course, that duty cycle signal is then fed into the switching converter itself. So we have the GVD as the duty cycle to output transfer function, that is basically the plant transfer function. Then we have the compensator transfer function, of course, and then we have the PWM transfer function, the GPWM, that's the transfer function of the pulse width modulator. So if we try to bring that together and write the formula for that closed loop system, we could say, let's start at the output voltage. How is the output voltage created? That consists of the error voltage, which is reference voltage minus output voltage. So here we have the error voltage. Then the error voltage is fed into the compensator, so it's multiplied by the compensator transfer function. Then it's fed into the PWM block, multiplied by the PWM transfer function. Then we have the duty cycle signal, and that is fed into the open loop plant transfer function. And then we are back at the output voltage. So that's the formula for the output voltage. And from that equation, we can now see, first of all, the loop gain, which is the product of all the gains in the loop. So if you look at the loop, and we have these three blocks, we have the GC, the PWM, and the GVD, as we had before. That's the loop gain. It's the product of all the gains in the loops. And second, we see we have the output voltage as a parameter and the reference voltage as a parameter. So we could calculate the closed loop reference to output transfer function. And if we do that, the closed loop reference to output transfer function, that's the gref out CL. So the CL stands for closed loop. That's output voltage over reference voltage, of course. And by restructuring the equation from the previous slide, we end up at the simplified equation that you can read in the second row, and that's gref out closed loop equals t over 1 plus t. And that's the typical closed loop transfer function form, where you have the 1 plus t in the denominator, where t is the loop gain, so the product of all gains around the loop. So when we look at that closed loop reference to output transfer function, and let's analyze what happens if the t is a large number. So we have a large number divided by 1 plus a large number, so that's close to 1. It means that the reference to output transfer function in a closed loop system is close to 1 if the loop gain is high. And that means that the output follows the reference, because the transfer function of 1 just passes through the changes that it receives at the input. And that's actually the goal of the control loop. So we want the output to follow the reference. The next transfer function is the closed loop input to output transfer function. So that's again the picture from open loop, so I messed up the pictures. So you can think of the compensator there. And here it says, there will be an animation that covers it, I think. Okay, so let's look first at the open loop input to output transfer function. We call that G in out. That's open loop input to output transfer function. We just assume that we have the transfer function from a model or from a mass or whatever. And then we close the feedback loop. And then we can say that a portion of the signal from input to output, a portion of the signal, that's the red part, goes directly through. So we have input voltage change directly appears at the output by the open loop transfer function. So that's the V out equals V in times G in out. And then the output, of course, is measured, and the change in the output also influences the output again by the loop gain. So we'll have the minus V out times T in addition. So that's then the equation for the closed loop input to output transfer function, and by restructuring that, we arrive at G in out closed loop equals output over input equals the open loop input to output transfer function divided by 1 plus t. So again, the 1 plus t is in the denominator, and if the t is is a large number, sorry, if the t is a large number, then we have some number divided by 1 plus a large number, and that's going to be a small result if the G in out is not a really large number, which it normally isn't. So we have a very small result, a very small transfer function, closed loop input to output, and that means that changes in the input will not appear at the output, they are rejected, and that's why the closed loop input to output transfer function is also called the PSRR, or the power supply ripple rejection or power supply rejection ratio. There are several names for that. We're going to talk about the measurement of PSRR very quickly also afterwards, but we will not do the measurement today. So the loop gain T of S. We said for a good regulation we need a high loop gain. If the T is smaller than 1, the loop gain will not have any effect anymore. That we can also see from the equations. Or if it's a small number, so close to 1 or smaller than 1. But the problem is that high loop gain for all frequencies is simply not possible. At some point we'll run into slew rate limitations or into gain bandwidth product limitations or whatever. So it's just not possible, and normally also not desired for the very high noise frequencies. Normally the loop gain is shaped to be a small number to not have the noise run into the loop or running around the loop. So normally a loop gain, a design goal could look something like that. We have on the y-axis the magnitude of the loop gain, and on the x-axis the frequency. At low frequency there is high gain, which is normally also limited by some maximum gain limit. And then it starts to fall, and it passes through the FC, that's the crossover frequency at the crossover frequency, and then at higher frequencies normally the gain is even further attenuated by placing an additional pole somewhere at half the switching frequency or something like that. So at low frequency the gain is quite high to achieve good regulation. This is especially important in the case of a simple voltage feedback, and then it crosses the 0 dB axis, that's the crossover frequency, and the slope at the crossover frequency should be around -1 or -20 dB per decade. When you have a slope of -1 or 20 dB per decade, then we can apply the simple phase margin test. We'll talk about that a little bit later. And the phase margin that is achieved is very close, or is getting close to 90 degrees. If you have a very high slope or a sharp slope, then the phase margin will be lower. So that's why a phase margin of -20 dB per decade, that's a good design goal. Yeah, so I already started to mention the phase margin test. When we look at the transfer functions of the closed loop, then in both cases, in reference to output and in input to output, there is the 1 plus t in the denominator. So what happens when the t tends to get to -1, then we'll have a problem, because we will have 1 minus 1 is 0, and 0 in a denominator is simply not good, or mathematically undefined, or close to infinite, or tends to infinite, and the behavior of the loop is no longer defined, it's unstable, and we don't want that. So by staying away from that -1 in the loop gain, we can check if the closed loop system is going to be stable or not. And that's of course a very simple test. One of the simplest stability tests is checking how much distance do we have towards the -1, towards the instability point. That's called the phase margin test, and here I would like to point out that this is only a special case of the general Nyquist stability criterion. That's a little bit more complex. I don't know it fully, I don't understand it fully actually, but in the general Nyquist stability criterion you have to look at the Nyquist plot. You have to check that you don't touch and also not encircle the instability point. And if you encircle the instability point, you have to uncircle it in I think the same amount of times that you did encircle it, or even more, I don't know. But yeah, we don't want that. And normally the systems in power electronics that we have here, the converters, they normally have a loop gain that is well behaved with a minus 20 dB per decade crossover frequency and a shallow slope. So not a lot of resonances and things like that. So we don't encircle the instability point, we don't touch it, we stay away from the instability point, and everything is fine. In theory, the test says if you have phase margin more than 0, so 1 degree, then the closed loop system is stable. And how do we measure that? The phase margin test says look at the 0 dB crossover frequency in the gain plot, and then measure how much phase distance is left before you hit the minus 180 degrees, because 0 dB, that's a 1. And the minus 180 degrees, that's a negative sign or changing the sign. So we end up at minus 1. That's the instability point. And by measuring the phase that is left before we would hit the instability point, we can get a number for the stability. You can also do that in a Nyquist plot. The Nyquist plot draws the same transfer function. On the left-hand side we see a Bode plot, on the right-hand side we see a Nyquist plot, where the x-axis is the real part of the transfer function and the y-axis is the imaginary part of the transfer function. And the minus 1 is directly visible at the unity circle, which is a magnitude of 1, and then on the left-hand side where there is the minus 1. And the crossover frequency, that's where the transfer function crosses the unity circle. And then we check how much phase is there left towards the instability point. So that's exactly the same representation on the left-hand side in Bode plot, on the right-hand side in the Nyquist plot. The Bode plot has an advantage that you can see the frequency directly. In the Nyquist plot, you don't see the frequency directly. You need to use a cursor to measure the frequency, for example. Yeah, I said before, we need to have more than 0 degrees of phase margin, but probably want to have a little bit more. And to illustrate that, we have done a simple reference to output step on a small signal model of a buck converter. So it's a synchronous buck converter in continuous conduction mode, and it steps down from 15 volts to 1 volt with a 300 kilohertz switching frequency, and the loop gain was adjusted where the compensator was selected to have 40 kilohertz crossover frequency. And then we gave it a step, and here you can see the step response. So there is quite significant overshoot and ringing. It should go from 0.9 to 1, but it shoots over more than 15% or something like that. And then there are several rings, and it starts to settle down. And if you look at that frequency in the step response, then you will see that this is exactly the crossover frequency. And the reason is that the crossover frequency defines the natural frequency of the closed loop system. So if you give it an impulse or a step, then it will react with its natural frequency. That's the crossover frequency. That determines the speed of the closed loop system. So that was roughly 7 degrees of phase margin. We have high overshoot and a lot of ringing, so that's probably not enough. Maybe there should be more phase margin. So how would it be with 23 degrees? Then it would be already better, but there is overshoot and there are several rings before it starts to damp out. At 30 degrees it's getting better. At 45 degrees even more, there is only like 1 overshoot and 1 more ring visible. And then at 70 degrees plus, you will end up in the highly damped or overcritically damped case where there is no ringing left anymore. So there is no ringing, and if you further increase the phase margin, then it will just become slower. So that's why a design goal for phase margin is typically somewhere around 60 to 70 degrees, or at least 60, or some people say 50. So it depends a little bit on how much overshoot is allowed and the trade-off between speed and damping. So the phase margin is a measure for the damping of the closed loop system. There is another value, that's the gain margin that we hear very often. Note that in a second order system, theoretically there is no gain margin because the phase never reaches the minus 180 degrees. In reality, there is always some parasitics, so it normally does reach the minus 180 degrees and there is some gain margin. And the gain margin is actually the amount of gain that would be necessary to make the loop hit the instability point. So if we look at the gain margin, in that case, that's around 20 dB or something like that. And then if we would increase the gain curve by these 20 dBs, or no, it's 40 dBs even, then the phase would hit the minus 180 and the system would go unstable. You can also look at that in an Nyquist plot. The minus 180 degrees crossover frequency, that's where the transfer function crosses the x-axis, the negative x-axis, and then the gain margin is the value that is left that you need to blow up the transfer function, that you need to multiply the transfer function with before it starts to hit the -1 instability point. Why should one measure the stability? Of course, to ensure stable operation at all operating points and at different environmental conditions. So minimum input voltage and maximum load and minimum load and maximum input voltage. So all these combinations. And then, of course, if there is a lot of temperature range, also at very low temperature, at very high temperature, or whatever, because the components can change. The low phase margin can add a lot of ringing to the system, especially if there are lots of load transients. Then there would be a constant ringing in the system. Every load step, the system, after each load step, the system would continue to ring with its crossover frequency, and that frequency would never disappear from the system. You would always see that. It could couple into other systems. It could pass through several regulators and degrade system performance. Especially when using linear regulators, there should be enough stability margin when powering clocks or op-amps or ADCs, because a badly damped regulator can even show up in an ADC result. And last but not least, to verify the design and simulation, as we said in the beginning, the simulation of small signal or of dynamics of converters is quite an effort, and to verify that, it makes sense to perform a measurement. How is a measurement working, or how can a transfer function be measured on the frequency response actually? The idea of a frequency response analyzer, such as the Bode 100, is that it generates a sine wave at a specific frequency, and that's added to a signal chain somewhere, so that's called here the add AC signal here, and then the signal passes through a series of transfer functions. It doesn't actually matter, and then the Bode 100 picks up a voltage at the input of a transfer function and a voltage at the output of a transfer function, and it calculates gain equals voltage at channel 2 divided by voltage at channel 1. And that's the definition of a transfer function. That's output voltage divided by input voltage. So the gain will equal the transfer function of the H2 block in that case. The path from the output to the point where the channel 1 is connected is not directly visible in the measurement. It will, of course, influence the signal. Can make the signal bigger if there is an amplifier. It can make the signal smaller if there is attenuation in that path. It could introduce additional noise. It could make the signal to noise ratio worse, but it will not directly show up in the measurement. Of course, it can corrupt the measurement, but it does not directly show up in the measurement. And if you assume that this add AC signal block that is the injection transformer, then you know why the injection transformer is actually not part of the measurement, so you don't need to calibrate it away. It makes sense that it has a flat frequency response, that it doesn't corrupt the measurement at some frequencies, but it's not directly part of the measurement and you don't need to calibrate it out. Then don't forget that transfer functions, of course, only make sense in LTI systems, so linear time invariant systems. If the system operating point changes over time, then the transfer function will not be measurable because the transfer function itself will change over time and the sweep takes some time, and during that time at least the system must stay in the same operating point. And for the stability measurements, note that in the switching converter there is only one duty cycle value per switching cycle. So the control loop can only react once per switching cycle, and that means that the loop gain or the stability does only need to be measured to half of the switching frequency of the system, because above half the switching frequency the compensator can't react to changes anyhow. A question that we receive quite often is calibration necessary? And for the loop gain measurements, normally not. The basic accuracy of the setup should be sufficient, especially if you use probes that are adjusted in the same way or compensated in the same way. You know your probes for channel 1 and the probe for channel 2, and if you compensate them once by using the trimmers, then the calibration is actually not necessary. If you're not sure, then simply check it out. Connect the output signal to both probes. So both probes are connected to the same signal, and then the result should be a 0 dB and 0 degree flat line over the entire frequency range, because there is no difference in the two signals that are picked up by channel 1 and channel 2. So now we'll step into more details. How is the loop gain measurement itself working? And here we use a method that is called the voltage injection method that was first presented by Professor Middlebrook I think in 75, year 75. And the idea of that is that the loop is not really opened, but that you insert an injection resistor into the loop at an injection point. So something like a 10 ohm resistor. And then the frequency response analyzer measures the transfer function TV, V for voltage, so it measures the voltage loop gain by measuring the two voltages on either side of the injection resistor. So that's the voltage injection method. Yeah, and of course that's very simple, and there is a lot of detail behind that, why that works. You can calculate a lot of math about that. You can make an equivalent circuit for the injection point. So you can say when looking backwards there will be a signal source that generates the voltage that is visible at that point, and after the injection resistor, so looking forward, there will be someone that picks up the signal that has an input impedance, and then you can work out the voltages and the currents at the injection point and calculate how the measured transfer function, the TV, correlates to the real loop gain that is present in the loop. And if you do that, you will find an equation that says the measured loop gain equals the real loop gain times the first term plus the second term, I call it here right now. And these terms are dependent on the ratio between the output impedance at the injection point looking backwards, so where the signal comes from, and the input impedance at the injection point looking forward, so where does the signal go to. And this first term is roughly 1 if this is a high ratio, and the second term is roughly 0 if the ratio is very high and the loop gain, or if the output impedance is a lot smaller than the input impedance, and if the loop gain that you want to measure is bigger than that ratio. So to summarize, when selecting the voltage injection point in a feedback system, we need to make sure that the input impedance looking in loop direction at the injection point is a lot higher than the output impedance looking backwards. And the measured loop gain must be bigger than that ratio. So the better the ratio is, the less we need to care about the measured loop gain. Of course, we also need to ensure that there are no parallel signal connections, parallel pathways where the signal could bypass the injection point, because then it wouldn't be part of the measurement. So it must be a one unique signal flow path. That's very often the case at the output of a voltage source, because there we have low impedance backwards. Then input of an operational amplifier, because there is high impedance forward at the input. An output of an operational amplifier normally has a very low drive impedance, and of course best between two operational amplifiers. If you have a signal conditioning chain in a bigger system, then between two operational amplifiers the measurement normally works really well without any problems. Yeah, we're gonna talk a little bit about the loop gain measurement now in detail, and Tobias will discuss where to put the probes and how to select the injection point in a couple of examples, and then we will go forward with our real-life demonstration.
Thank you very much, Florian. Here we can see that the Bode 100 is connected to the B-bit 100, which is the injection transformer. This one is connected to the injection resistor. Then channel 1 is connected on the feedback side, so they are the feedback resistors. And then we measure from channel 1 across error amplifier, compensator, through the gain, through the complete system to channel 2, which is connected to the output side of our regulator. So now we will have some practical examples. If you have some questions during the examples, please just send us these questions in the Q&A function of WebEx. So first of all, this is the VRTS board of Picotest, which does have a linear regulator, and the output voltage is 3.3 volts. So there's the input voltage and the output, and there we have the linear regulator. Then we will have a look where are the feedback resistors. There we can see it, R3 and R4, and as we can see there is R2 already put in, which is an injection resistor. Here you can see the setup. Bode using the B-bit 100 for the galvanic isolation. We connect it to the injection resistor, channel 2 on the output side, output voltage side, and channel 1 to the feedback side. Both grounds of the probes are connected to the common ground on this linear regulator. Second example, we have a step-down converter, also demo boards. As always, I have a look where is the feedback. You can see pin 20 is the feedback pin. There we have the feedback resistors, and then we can directly see where we have to inject the signal, or first of all put an injection resistor, because on this board there is no injection resistor in the layout already, so we have to put one in. Setup is always channel 1 and channel 2, and the ground connected to common ground. For the injection resistor we normally use 5 to 10 ohms, but afterwards in the presentation where we discuss how big the injection signal should be, there are further details on the injection resistor.
There is a question, Tobias, that I'm going to read right now. The question is, when you do a calibration of the probes, where do you connect both probes? Is it best to do it on the feedback side or on the output side? And I try to immediately answer that. In my opinion, it's best to do it not in the circuit, but directly on the signal source of the Bode 100, because then you will have a clean signal without any noise and without any disturbances. So I wouldn't do it in the circuit, I would do it out of the circuit directly at the output of the Bode 100.
So similarly as you have seen in the picture before, where you can see how to check if the probes are, if you need calibration or not.
Exactly.
So the next example, we have a Flyback converter. Here we have the converter itself. We have the feedback resistors, but we have to go look a little bit backwards so that we don't have any parallel signal path, and then we can find the output voltage and a very good point, which is R15. In this case there is already resistor in the demo board, which is a 0 ohm resistor, and if you want to do the the signal injection, you need to just change this 0 ohm resistor with a 5 to 10 ohm resistor, and then you can inject the signal. A further example, a voltage loop gain example. There we have an LED driver board which has a current output, high side shunt resistor, and which will go to the amplifier, the op amp, and to check if this is a good injection point, you see the shunt resistor is normally very low in resistance, so this is a good point, and the input of a differential amplifier or just an op amp has high impedance, and therefore this is a good injection point. In this case, we don't have a common ground, and therefore we need differential probes, which are connected to the injection resistor and to the negative path. There's a little bit more practical example. There's the more practical demo board, which is also an LED driver. There's the I-sense positive and the I-sense negative pins, which are connected to the shunt resistor. And as you have discussed in the example before, we can put an injection resistor on the positive side, and then the differential probes are connected between the injection resistor, and the ground part, the second part, is connected to the negative side of the I-sense.
Yeah, before we start into the live measurement or into the demonstration that we have prepared for you, there is something that confuses very often, because from now on you can forget that I said we measure the phase margin as the distance towards minus 180 degrees, because from now on we measure the phase margin as the distance towards the 0 degree line, so the 0 degree phase. And the reason is that the system that we are measuring is running closed loop, and we inject a disturbance signal into the closed loop system and measure the loop gain in that system. And the signal that we inject runs through the inverting error amplifier, and it gets a 180 degree phase shift. And that's the reason why the instability point in the measurements is at +1 and not at -1. I'll try to explain it in a little bit different way. On the left hand side you see a feedback loop that is opened, so the summing node did disappear, or did want to take out the summing node, and the open loop gain normally is defined as the transfer functions of the open loop, so T times H in that case. That would be the open loop gain. What we measure in our measurement, you can see that on the right hand side. The summing node, that's part of the error amplifier, it's the inverting amplifier, that's still in the system, and we break it at the feedback side and then inject the signal there. The signal runs through the transfer function block H, it runs through the inverting node of the error amplifier, it runs through the G, and we measure minus G times H. And this minus is the additional 180 degree phase shift. It causes that the instability point, or the positive feedback point, actually is at +1 in the measurements. So we can directly read the phase at crossover at the crossover frequency, and that's the phase margin. You don't need to subtract a value or something like that. Maybe another explanation: if you assume that at that point the injection voltage here is changing, and then the voltage runs through the system and it comes back to the output with 0 degree phase shift, but amplified, then it will go in bigger, and it will go around the loop getting bigger and bigger and bigger all the time. So that's why positive feedback in that case, when we measure the loop, appears at 0 degrees and not at minus 180 degrees. Something very important in addition is the injection signal size. The small signal models that are normally created to model the dynamic behavior of a converter and that are used to design the compensator are linearized, because the systems normally aren't linear. So they are linearized in the operating point, and of course linearized things are only linear for small signal changes. If you have big signals, then you will bring the system out of the operating point and will measure large signal effects. Small signal and linear means that the measurement result must not depend on the signal size. So you can check that quite easily by first choosing an injection signal level and make a measurement. Then reducing the injection signal by, let's say, 10 dB. And if the signal or if the measurement result changes, then the signal level was too high. And to check if it's still too high, you can again reduce it. And if it doesn't change, then it's low enough. If it still changes, you need to further reduce it until it doesn't change anymore. And to check if you're in a linear region, you can try to increase it again a little bit. If the result stays the same, then you're safe. You're in a small signal region and you're not measuring large signal effects that come from slew rate limitations or something like that. Yeah. So if you look at the picture on the left-hand side, so this is a typical picture for an overdriven measurement. There are discontinuities in the results. They are very strange. That's not plausible actually, or it shouldn't be like that. And by reducing the injection signal level, here it was reduced by 20 dB, I think, the result is now getting clean. But when you reduce the injection signal size, then there will be more noise on the measurement result, especially at low frequencies where the gain is high. The measurement is prone to noise because the loop pushes the entire injection voltage to one side of the injection resistor. So on the other side there is nothing left to measure. And then trying to measure the phase between two signals where one is nearly not visible and the other one is very high, that's very difficult. That's why you see noise on the measurement curves, especially where there is high gain in the loop. And to overcome that, you can use the shaped level function, or you can shape the level, a variable signal level over frequency. In this case, for example, you can see that at 100 Hz, the signal level was at 5 dBm, and then above 500 Hz, the signal was constantly reduced, and above 2 kHz or 3 kHz, it was at minus 20 dBm. And with a change of injection signal level like that, you can avoid saturation in the higher frequency areas where the system is sensitive to the slew rate, and overcome the noise in the lower frequency areas where you need more drive signal to get the measurable result on the one side of the injection resistor. Some other things to consider. Don't forget that the DOT, or that's the system under test, is a part of a complete signal chain. It will have a supply that has some output impedance. It will have an input filter. It will have a load. And all these things can influence the system itself. It can change the transfer function. The input filter can cause instabilities. We will talk about that in another webinar. The load can change the plant by adding more capacitance, for example. The operating point can influence the plant transfer function. If I have a very nonlinear system, changing the operating point will change the frequency response of the system. So you have to measure the loop gain under all expected load conditions with the input filter connected. And please please take care if you use electronic loads. These can cause strange effects as well if their control loop interacts with the system. So you just need to take care there. We normally use resistive loads if possible. We also said we're going to mention how to measure the plant of a system, and that's pretty easy, at least in analog control. So in this case, we see again our buck converter that has an analog control, in this case voltage mode type 3 compensator, and you just need to move the channel 1 connection point from the injection resistor to the comp pin, and then you will get the plant including the PWM compensator. The Bode 100 measures the transfer function from the comp pin to the output voltage. That's the plant including the PWM generator. If you want to measure the compensator in analog control, that's the same. It's pretty easy. The channel 1 is connected at the input of the compensator. That's the feedback side of the injection resistor, and the channel 2 is connected to the comp pin, and that gives you the transfer function of the compensator. In a digital system, it's a little bit more complicated because the COM pin doesn't exist as a pin where you can connect the probe. It's inside the processor, it's a number, a digital number, and the output of the digital compensator is normally the duty cycle signal. So a trick is that you can use the normal loop gain measurement and set the compensator to have a gain of 1, and then theoretically it falls out of the picture and the loop measurement equals the plant. Of course, the digital system will introduce some time delay that you can see as a phase delay later on. If you want to measure the line to output transfer function, closed loop, or the PSRR, you somehow need to modulate the line. That's a little bit more tricky. There are two possibilities from Picotest. They are called the line injectors. There is the J2120 that can handle up to 5 amps and 40 volts, and the J2121 that can handle up to 20 amps and 400 volts. And then the input, channel 1, is connected to the input voltage of the converter, and channel 2 is connected to the output voltage of the converter, and that gives the closed loop line to output transfer function, or the PSRR. Okay, so let's directly head into the live measurement, and we'll use a SEPIC converter from linear or analog. It's a demo circuit 1342B. It is a SEPIC converter that has an input range from 18 volts to 72 volts and generates 24 volts output at 1 amp load current with a switching frequency of 300 kilohertz. And when I first measured that SEPIC, then we found that the crossover frequency is around 8 kilohertz and that the phase margin was more than 65 degrees in all operating points. So it's a very stable control loop design, but really boring to show in a webinar. So we modified the control loop, and just a short explanation on how to make the things more interesting. First of all, we did simulate the system in Breach WDS. That's a power supply or a control loop design software, and actually complete power supply design software. And then we have verified the simulation using the Bode 100. Then we have modified the type 2 transconductance compensator to get less phase margin, actually, so to make it worse. And I did solder the new component values to the board. So the R6 and C11 and C12, no, only R6 and C11 were changed from 30 kilo ohms to 100 kilo ohms, and 4.7 nanofarads to 1 nanofarad. C12 did stay at 100 picofarads. And with that, we could bring down the phase margin to make it a little bit more interesting for the stability measurement, especially for the transient response. Yeah, for the loop measurement, actually, it doesn't matter. But in the transient response, you don't see anything if the system is stable. You don't know why it's stable, you just see it is stable. So we're going to measure the loop of the 1342B, the SEPIC converter. And here we have the input voltage. Then it's a first inductor, coupled inductor, the coupling capacitor, the second inductor, and here we have the output capacitors and the feedback divider with 280k on the top and 20k on the bottom, and the injection resistor again is placed on top of the feedback divider that gives the loop gain. So we're going to do that in reality. Toby, can you please explain the connection setup and then connect the Bode for the loop measurement?
Yes, for sure. Here we have the Bode 100, which is connected to the injection transformer. From there, we connect it directly to our demo board, which you can see here. On the left-hand side, there's the power supply for the demo board, there's the input voltage, and on the right-hand side, we've connected a resistive load. And there's also 2 digital multimeters to check the output current and the output voltage. So now I connect the injection signal from the output from the Bode to the B-bit to the injection point. We already have soldered the resistor and 2 pins on it so that we can connect it easily. First connect the output, that's the disturbance signal. Then I use the probes. First of all, channel 1, which is connected to the feedback side. And then I have to connect ground. and channel 2 is connected to the output voltage side. So, done that now. Now I will switch on the power supply. So we have 40 volts input voltage, and the output current, the output voltage is about 24 volts and 0.3 amps of output current. Now we can switch to the Bode Analyzer Suite and to the settings to do the measurement.
Okay, so gonna start the Bode Analyzer Suite. And if you start the Bode Analyzer Suite for the loop gain measurement, you use the gain phase measurement mode. That's a very simple measurement mode where the predefined settings normally match pretty well what you need. And first we choose the frequency range of interest. I know that the crossover frequency is around 10 kilohertz, and I know that the switching frequency is at 300 kilohertz. So we're gonna measure from roughly 100 hertz to 200 kilohertz in that case. So let's enter 100 hertz here and 200 kilohertz at the stop frequency. Then we can choose a linear or logarithmic sweep, but log is fine in that case. For a Bode plot, the number of points 201, that should be enough also. The level we leave constant for now at 0 dBm, and then the receiver attenuators, in this case we can set them to 0 dB, so the maximum sensitivity of the input channels. Since we use 10:1 probes at the input, we don't need to further attenuate it in the Bode 100 itself. The receiver bandwidth can be set from 1 Hz to 5 kHz. This value determines how narrow the input filter will be selected. It's a frequency sensitive measurement. If you use a very narrow filter, then it will reject a lot of noise from sidebands, but the measurement takes longer. And if you use a very wide filter, the measurement will be very fast, but it will also include a lot of noise from the sidebands. And a good value to start is 100 Hz. That gives you a good trade-off between noise rejection and speed, in my opinion. So I think we're set up.
Yes, everything is running.
Everything is running. So we'll start a continuous sweep in that case. So let's play continuous. And then I click on auto optimize here. And the loop measurement is already visible. So the first thing we need to check is the injection signal level size. So as I said before, we need to make sure that the result doesn't change when we change the injection signal level. So I put that curve into the memory and I lower the source level by a factor of -10 dB, and then we check, did the result change? So yes, the result did change. As you can see here, it has changed. So the system was still overdriven a little bit. There was too much injection signal that we put into the system. So I'm gonna update the memory here and then further reduce it to -20 dBm, and then we'll see what happens. So we see the result is still changing. We are in an operating point where the system seems to be pretty sensitive to the injection signal level. So it has still changed. We need to further reduce it. I update the memory and I reduce it to -30 dBm. And now we are at the minimum voltage that we can apply in that case. And now the result did not significantly change anymore. So from my point of view, the -20 dB is low enough because the change was very, very small, nearly insignificant. It would be like a couple of tenths of dB and maybe a couple of tenths of degree, but I don't care. So let's go back to the -20 dBm. And what we have seen in addition is that the noise at the low frequency did grow. The lower we set the injection level size, the more problems we have in the high gain area, where actually the control loop pushes the entire injected signal to one side of the injection resistor and the other voltage is very, very small. So in this case, with around 60 dB, that's a factor of 1,000, only a fraction of the several millivolts that we inject will appear on the one side of the injection resistor, only some microvolts, and these microvolts are buried, or hundreds of microvolts are buried in the noise and the ripple from the switching regulator, and it's really difficult or nearly impossible to detect the phase in that case. So that's why we need higher injection signal at low frequencies. And we're going to do that by using the variable signal level. So I switch the level to variable, and then I click on shape level, put that a little bit aside here, and now I can change the injection signal level with frequency. And from the results I can see that the noise starts to appear below 1 kHz. And so I double click at the 1 kHz to create the point here, and then I double click at 100 Hz and maximum level to increase the injection signal level at lower frequencies. And at low frequencies the system is not sensitive to the signal level size. Yeah, at DC you can change it from anywhere to anywhere. At low frequencies there are no slew rate limitations or others. So now I close and I update the memory here, and now we have a measurement that runs from roughly 65 dB to minus 30 dBs, so nearly 100 dBs of range, and it runs in 5 seconds. It completes the sweep, and that's pretty nice. If you want to further reduce the noise, you can reduce the receiver bandwidth, but then the measurement, of course, will also be slower. In this case, I just leave it like that, because in the next step, we will analyze various operating points, and then it's just nicer if the sweep runs fast. And I actually don't care so much about that noise at the low frequencies in this case, because the important point is here at around 15 kHz. That's where the crossover frequency is, and that's where the stability margins are measured. And for that, I go to the cursor ribbon and I select the cursor calculation, stability margin calculation, and I say track margins, and then the Bode Analyzer Suite shows me we have 53 degrees of phase margin, 26 dB of gain margins, and a stability margin or vector stability margin of 0.7. That's, by the way, the closest distance to the instability point. Okay, so we'll continue by analyzing that system over various operating conditions, and I'll put on the camera. So we're currently, or first I name that memory here, currently we are at
41 volts.
40 volts and
0.3 amps
0.3
the output.
Amp output current, and yeah, that's it basically. And now I switch on the camera so you can see Tobias will now change the input voltage to the maximum input voltage.
Exactly, now I will change the maximum input voltage is 72 volts, so we'll increase it to about 70. Now I have 70 volts, and the output current is still at 0.3 amps.
Okay, so the curve is already done. I'll put that into the memory. That's 70 volts and 0.3 amps. Now we could go to...
Does the phase margin has changed?
Ah yeah, phase margin is now at 46 degrees. So before it was 56, now it's 46 degrees. Can you please go to the minimum input voltage?
Minimum input voltage is 18 volts. So now we go down to that. Now at 20.
Okay, so now we are at 20 volts, and now you can see here at the crossover frequency things start to change. The phase starts to roll off quicker, and we end up at a phase margin of 32 degrees. So that's not so nice anymore. I'll enter that into the memory and I call it 20 volts and 0.3 amps. And now we're gonna increase the load current to 1 amp.
So now I will change the output current using this resistor or resistive load. And now you can see the output current, which is now at about 1 amp.
Okay, I'm gonna put that down, and then we can see now the phase margin is really low, so now we do have a problem here. Phase margin is at around 9 degrees, so that's now really bad. And I put that into the memory and I call it
20 volts,
20 volts
1 amp,
and 1 amp, and that's around 9 degrees phase margin, and we're gonna increase now to 40 volts and afterwards to 70 volts. Can you please increase to 40 volts?
Input voltage is now 40 volts. Sweep is done.
Okay, we'll put that into new memory. We are now at 26 degrees of phase margin, and that's 40 volts and 1 amp.
You can see the maximum output current is changing the phase margin quite a bit. Lower it.
Okay, and then we're still missing maximum voltage and maximum current.
So now we go maximum voltage. Now we're at 70 volts and 1 amp the output.
And phase margin is at 30 degrees. That's 70 volts and 1 amp. Okay, and that's basically it. We have a family of loop gain curves, and we have done that in a couple of minutes right now. Of course, they are not beautiful because that's a trade-off between speed and noise. You can now reduce the receiver bandwidth to clean up the curves. You can use a 10 Hz measurement, but the 10 Hz measurement will not take 5 seconds. It will take, let's wait a little bit, and so it takes 50 seconds. Yeah, so that's why we didn't do it right now, but then you will get a less noisy curve. So as a next step, we now will measure the compensator, I think. Let's have a look at the presentation. The next step is measuring the compensator, and for that we move the channel 2 connection from the output voltage, so from the upper side of the injection resistor, to the comp pin. So I put on the camera.
So I'll do it now. So
I'll put that into memory here.
Channel 2. First of all, I will switch off the device under test so I can't break anything. And change channel 2 from the output voltage to the compensator pin and switch on power supply.
Okay, and now the measurement, I will speed up that again to 100 Hz. And now we have the transfer function of the compensator. I'm gonna switch off most of the curves, only the one that is in the same operating condition. So that's now the compensator, I call it compensator. And this one, I think here we can increase the level a little bit. That shouldn't make a problem. Should get a cleaner result here. We can change the result and get a cleaner curve. The result itself didn't change, just the noise has reduced. So this part is not so sensitive to the injection signal level. We update that. And now we're gonna measure the plant. So, and there I think we have to reduce the level again. Let's have a look. The next measurement is gonna be the plant. And for the plant measurement, we put the channel 1 at the comp pin and channel 2 at the output pin.
So now I have to change that. Channel 1 goes to the compensator pin and channel 2 go to the output voltage, so top of the injection resistor. I've done it and switch back on the power supply.
Okay, and that's the plant measurement. And now I need to check if I didn't use too much signal level. Gonna store that to the memory and call it plant. And then I'm gonna reduce the level a little bit to see if something changes. Yeah, there it did change. It was too high. So let's reduce further. Okay. Now it didn't change anymore. So we're done. That's the plant measurement. And now we can do a really nice thing. I'm gonna do that. We've tried that in the morning. It did work pretty well. Hopefully it works here again. So I'm gonna add a new trace. And then on this picture on the right hand side, I'm gonna use a math trace, and I will say, let's do compensator multiplied by plant, and then that's the loop. So it's very similar. The red curve, that's the math trace, is very similar to the meshed loop. Yeah, the loop consists of compensator multiplied by plant. So that's really nice. It matches the loop measurement from before, that was the violet curve, pretty well, really nice. So that's just a mathematical operation. Yeah, so I think we're done here, and the last thing that we want to show in our webinar today is the small signal load step response. And I call it a small signal load step response because we want to compare it to the Bode plot that we have measured right now. And that's small signal measurements, so we also need to do small signal step load response. And we're going to do that by using a J2111A current injector from Picotest that is generating repetitive small signal load steps, and we measure them on a scope, and then we can use averaging to get rid of the switching noise, and then we see the dynamic behavior of the system. And Tobias is now going to set up that measurement.
So we here have the current injector from Picotest, which is the modulation input is connected to a waveform generator. This waveform generator is set to a square wave of 1 kilohertz, and the signal is 4 volts peak. Then we have a current monitor, which is directly connected to the oscilloscope so that we can see the step load as well, of the step from the waveform generator, which is drawn from the output of this SEPIC converter. And then the output pins are now connected to, switch off the power supply, to the output of our device under test. But we also have to connect the oscilloscope, another probe. That last point, now ground. Ground is now connected. Then I have to switch on device under test and the output of the waveform generator.
Okay.
Now that's it.
So I'm gonna bring on the scope on the screen, and here we can already see on the lower graph of the scope, that's the current steps that we are drawing. So it's 40 milliamps current steps, and on the channel 1 or on the top side we can see the response of the system with the little overshoot and slight ringing. Remember, we have now a setting where we have roughly 30 degrees of phase margin. So that's why we see a couple of rings up there. And if we now change the system to the worst case with 9 degrees of phase margin, then we will see that the ringing is significantly increased. I think that was at the minimum input voltage. Tobias, yes, can you please change that?
To input voltage of 20 volts.
So we're still drawing 1 amp of current at minimum input voltage of
now with
20
18
volts. 18 volts. So that's really the minimum where it still should work. And now when we look at the scope, we can see that there are really several rings, 1, 2, 3, 4, 5, 6, 7 rings before the ringing really disappears, before it's completely damped. And it takes a long time. There is more overshoot, and especially the ringing is an issue that shouldn't be there. Yeah, I think let's have a look at the presentation, but Did we forget something, Tobias?
I don't think so, no.
There are several nice readings where we have drawn all the information from. You can read it yourself if you want.